Hello everyone. So I'm going to demonstrate our lab 03. So the experiment title is Study of a 741 operational amplifier as Inverting Adder, Integrator and Differentiator. So the objectives of this experiment are actually to construct an inverting adder, an integrator and differentiator. And we are going to simulate this environment in PSpice. So in PSpice, we basically need these components. So I will demonstrate, don't worry. So next thing is the pinout diagram. I think you already done two experiments related to this 741 op-amp, so you already know. Anyway, so number 2 and 3 are the input pins. One is inverting, another is the non-inverting, and pin number 4 and 7 is required for biasing purpose, that is powering the op-amp, and 6 is the output pin through which we can get our desired output. So next, first circuit is the inverting adder. So previously you already learned about inverting amplifier. So the circuit was similar to like this. So if I explain, so in case of inverting amplifier, there was only one voltage source, let's say this type, and then other things are similar to inverting amplifier. Okay, this is more like an inverting amplifier, and for inverting amplifier the output expression was, if you remember, minus RF, that is the feedback, divided by input resistance RI1 into our input voltage VI1. And now we are talking about inverting adder. That means we are going to add multiple voltages. So that's why we want to supply multiple voltages. So in this circuit, we actually supply two voltages. One is V1 and another is this VI2. So let me clear the screen. So now this is the expression. So if you can recall, previously only this portion is similar to inverting amplifier, and now we are working with adder, that means multiple voltages. So similarly another voltages is added with you. So if you drive the expression for these circuits, then obviously you will find this type of expression, and I believe probably you already learned this derivation in your theory class, or you are going to learn. So don't worry. So I can say in case of inverting adder, we generally add multiple voltages. Before adding, they are generally multiplied by respective gains, and gains are provided by feedback resistance and their input resistance. So for VI1, okay, so for VI1 the feedback was same, it is 10k, and it is also 10k. So if you put this value, so here obviously 10 divided by 10 minus sign, and then also for RI2 I have written here 10k, so that means it is again 10. So both one, here it was VI1 and then VI2. So you can easily drive this. So the output expression is V output equal to minus VI1 plus VI2. So for this circuit configuration, we are just adding those two voltages, and it is an inverter operation. That means it is going to be inverted. We have connected this to negative terminal. That's why it is minus. So if I want to predict what will be the output voltage, so as you can see, this is 5 volt and this is actually minus 7 volt, because I have connected minus terminal to this. That's why the output voltage will be 5 minus 7 volt, then there is another minus here. So the output will be total 2 volt. So when I will perform this simulation, you will look that the output I got is plus 2 volt. So this is the inverting adder, and another name of this inverting adder is called summing amplifier, because it is summing different voltages and also it is amplifying, and the gain is one is RF by RI1, another is RF by RI2. If I add another voltage, then the expression should be plus RF divided by RI3 into VI3. So this should be the expression for 3 voltage source. And this procedure and report question I will demonstrate when I will show you the demonstration in PSPice, so don't worry. Our next circuit is the integrator circuit. So far all the circuits that you have noticed are based on feedback resistance, but in case of integrator and differentiator, we have used, for integrator we have used feedback capacitance, and for differentiator we will see later that we will use a capacitor in the input. Anyway, so for now in this integrator circuit we have a capacitor as the feedback, and other configuration is just like other inverting amplifier, this whole picture. And for input we have supplied a V pulse. So in second experiment I think you already used V pulse, so it will be easier for you, don't worry. So anyway, if I go to the output expression, so this is the output expression when you will derive the expression for this circuit, you will generally find this. So this is just easy derivation in your theory, I think you will read. So here is the input voltage and here is the output voltage. So if you derive the relation between this input voltage and output voltage for this resistance and capacitance as feedback, then you will find the expression of output voltage is just like this. So what does this integration means? It is just like the integration that you have taught in math classes. Anyway, so for this circuit we will generally provide a rectangular pulse. So let's say the rectangular pulse is just like this. So what do we mean by integration? So I can say if this is the voltage axis and this is time axis, and if it is 5 volt, let's say, and it is minus 5 volt. So if I write a mathematical equation for this portion, let me choose another color. So if I want to write an equation for this portion, then the expression will be V equal to 5, right? Because it is parallel to T axis. So the expression will be V equal to 5, and if I integrate this voltage, and you know the integration is just 5 and we are integrating with T, that is dt. So the result will be 5t. So if you now plot this 5t, then obviously it will be a straight line that is crossing 0 0. So this will be like this, and in the expression we have a minus sign in front of this. That's why the output will be actually if I erase it, okay, so the output will actually in this direction. Why? Because we have a minus sign in front of this. So for this portion the output will be like this, and for this portion if we want to write the expression, then it is v equal to minus 5. So minus 5 dt, if we integrate this, the result will be minus 5t. And again, we have another minus here. So the final expression will be 5t. So the expression will be like this. And it is shifted, that's why, from the here. So now it is easily observable that if you supply a square wave, then the wave you got is a triangular wave. So in this integrator circuit, here we have supplied a square wave as written here. So if we supply a square wave, the output what we will get will be a triangular wave. We'll observe this in the PSpice simulation. So let me clear this all. So this circuit I just explained. Also you can choose to provide sine wave. So if you provide sine wave in the input, so obviously if you integrate sine, then the result will be cos. So if you provide sine wave, you will get a cos wave and it will be minus cos, and in the output expression we have another minus, so it will be plus cos wave anyway. So you can verify this. So another important point, how to use this square wave using V pulse. So there was another video in experiment 2, I believe, where it was demonstrated how to make a triangular wave using V pulse. So that is more like similar. For example, we want 5 volt amplitude, that means 10 volt peak to peak and 500 hertz frequency. So for 10 volt peak to peak, I may provide V1 equal to minus 5 and V2 equal to 5. And we want a square wave. So this is just like this. So obviously, initially we don't want any time delay. That's why we have provided 1 pico. And obviously, we don't want any rise time and fall time. So it should be 0, and for PSpice purpose, we generally provide it very small value, that is 1 pico, and the pulse width, that is this duration. So total period will be 2 milli, and why 2 milli? Because our frequency is 500 hertz. So 1 over 500 hertz, that will be 2 millisecond. That's why our period is 2 millisecond. And if it is the period, then if it is 2 millisecond, then for 1 millisecond the pulse will be higher, and for second millisecond pulse will be lower. So I can say the pulse width is 1 millisecond. So that's why you need to configure V pulse according to these parameters. I will show you in the PSpice, so don't worry. And this procedure and report question I will demonstrate in the PSpice. And our last circuit is the differentiator circuit. So just like an integrator, in the differentiator we also need capacitor, but there is a difference. In integrator we have used capacitor as the feedback, but in case of differentiator we need capacitor at our input side and a resistance in our feedback. And if you drive the output expression, then the expression will just like this. So here the input voltage is differentiated. So initially I have shown you that if you provide a rectangular pulse, that means if you integrate a rectangular, the output will be triangular, right? And you do know that differentiator is just the inverse of integrator. So in this differentiator circuit, we will provide a triangular pulse. So here triangular wave we will provide as the V pulse, and the output what we will get is a rectangular pulse, because differentiation of triangular obviously gives a rectangular pulse. Also in mathematics, if you want to justify it, let's say this is a triangular wave. So for this portion, I can say this is more like, let's say, uh, 5t. So if you differentiate this, obviously t will be vanished. So it will be a straight line. So that's why the output of this will be a straight line for this portion, and again it will vary. Anyway, I will demonstrate this in the when I will perform the simulation in PSpice. And to have a triangular wave, I think you already used this in previous experiments. So anyway, for 500 Hz, similar to rectangular wave, obviously the period will be 2m, and these three things are different for rectangular. So obviously for triangular, we need some rise time and also we need some fall time, and there won't be any pulse width. That's why I have written pulse width equal to 1 pico, that is close to 0, and the rise time will be half period, and similarly the fall time will be the second half period. That's why 1 millisecond rise time and 1 millisecond fall time. So this will give you a triangular wave as input, and if you provide this triangular wave, the output you will get a rectangular wave. And for these circuits, for these two circuits basically, one is this differentiator, second one, and another is this integrator, we will generally focus on the output wave shapes, because in practical scenarios and in other cases, the circuits should be more complex and we need to integrate other components. For example, in practical scenarios, we need to add other resistance here. So we are not demonstrating this, and for this we will, as I mentioned, we will only follow the wave shape. So anyway, the procedure and the report question I will demonstrate in the experiment when I will perform the simulation in PSpice. So stay tuned.